In this example, we consider a simply supported beam subjected to a couple applied somewhere in the middle of the beam. The purpose of this example is, of course, to solve it, but also to expose another fundamental aspect of analyzing beams, namely continuity conditions. So, a simply supported beam of total length L is subjected to a couple M0, and the couple applied somewhere in the middle, and the beam is divided into two segments, A and B. Our task is very basic. We need to determine the deflection curve. We will solve this problem by solving the second order differential equation, where on the right-hand side we have the bending moment function. We can solve this function using standard procedures for generating bending moment diagrams. In particular, we draw the free body diagram for the entire beam, denote the reactions RA and RC. Then we write sum of the forces on Y and sum of the moments about A. And I want to pay your attention that here we have A plus B, which is of course L. And as a result, we obtain the following answers for the reaction forces. These answers are very easy to interpret. The forces RA and RC form a couple. Since the distance between the forces is L, it is easy to see that the magnitude of the couple is M naught, and of course the M naught generated by the two reaction forces exactly balances applied couple M naught. We proceed to the bending moment functions, and as with the bending moment diagram, we will deal with two segments. The first segment is when X is to the left of the applied couple M naught. So in this case, the free body diagram corresponding to a cut at the generic location X has the reaction force and two internal forces, and therefore the equilibrium equation for the moment about the point F, which is the point where we make a cut, gives us two terms, and as a result we find that the bending moment is given by this expression. Next, we proceed with the cut when X is between A and L, meaning the cut is to the right of the applied couple M naught. In this case, the free body diagram looks like this. So we have the reaction force, the applied couple, and two internal forces. And now we write down some of the moments about G, and we obtain the following equation. And the answer for M of X, I want to pay attention that I did not write down some of the forces on Y. And the reason for that is quite simple. All I need is M of X, right? I don't need V of X. So now I can write the differential equation, and we write it in the form which emphasizes that the expressions for the couple are discontinuous, right? So we have two branches, one valid for x less than a and another for x larger than a. We can make a similar statement by introducing two branches of the solution. So I will be calling the branch to the left of A as V minus and the branch to the right of A, V plus. So here we go. So we rewrite this equation in this form, right? So V minus uses this term and V plus uses this term, right? So instead of having two branches in the right-hand side, we just created two branches of the solution B. Right now, it's nothing but a matter of formality, but it will help us with solving the problem. So let's see what we get. First, let us re-examine the boundary conditions. The boundary conditions are imposed at 0 and L, where, of course, we have to acknowledge that at 0, the solution is given by V minus. At L, it is given by V plus, and therefore we write V minus of 0 and V plus of L. Both of them are equal to 0. Next comes something really critical for this problem. We need to talk about continuity conditions. Basically, we put aside the point where the two branches of the solution meet, and now we need to address this point directly. What I claim is the following, that if I look at the deflections at this point, then the deflection on the left, which is represented by V minus, is equal to the deflection on the right. How do I argue that? I said if they were different, then the beam would be broken because the two parts of the beam can move different distances. And therefore, since the beam is not broken, V minus must be equal to V plus. Similarly, I claim that the slopes on the left and on the right must be the same. Okay. This would not be true if we had a hinge. You may think about your arm and you may think about the elbow as the hinge. And then the upper and lower parts of the arm can move independently and the angle will not be continuous, right? We simply can bend the arm. But there is no hinge here, right? And since there is no hinge, the curve must have continuous slope or theta minus equals to theta plus. Similar to the boundary conditions, we would like to translate the continuity conditions from the physical form given in terms of the displacement and angle into the mathematical form that involves the function v and its first derivative, v prime, because mathematically that's what we want to do when we deal with solving the differential equation. So this slide is the single most important aspect of solving this problem. It's basically the single new aspect of this problem. Let us try to put it together. So first, we look at the differential equation for V minus. That's the equation we start with. And then we differentiate it 2 times. First, we have a constant C1. Then we differentiate one more time, and we obtain also the constant C2. We do pretty much the same thing for the right branch. That's where we start. That's the differential equation. We integrate it once. We have a new constant. I call it C3. We integrate it one more time. We get another constant, C4. So if I look at these functions, I see that there are 4 constants, C1, C2, C3, and C4. The algebraic equations that will allow us to determine these constants involve 2 boundary conditions, x equal to 0 and x equal L, and 2 continuity conditions at x equal to A. So in total, we have 4 constants and 4 conditions, 2 continuity and 2 boundary. So we're in good shape. Let us see how it's implemented. Start with the boundary conditions. I take the function v minus and evaluate it at x equal to 0 and equate it equal to 0. So this equation is very easy to evaluate because this term is 0, this term is 0. It means that C2 is equal to 0. Very simple equation. Then I take the equation for v plus and evaluate it at x equal L. It's a little bit more cumbersome equation than the first one, but nevertheless, not a big deal. Now let me proceed with the continuity condition. I start with the condition that v minus and v plus at A are the same. So that's the expression for v minus. I evaluate at x equal to A. That's the expression for v plus. Evaluate at x equal to A. And that gives me the third equation. And finally, the fourth equation. I take the derivative of v minus, which is this. Evaluate at x equal to A. And equate it to the derivative of v plus at x equal to A. The bottom line is I wrote down 4 equations for 4 unknowns, C1, C2, C3, C4. If I solve equations, I obtain the following values for the constants. I want to pay your attention that the very first equation gave me C2 equal to 0. Here, of course, it is. The rest of them are not 0. And now I can take these constants and I can go back to the equations for v plus and v minus, and I can write down explicitly the answer. The answer, of course, involves 2 branches. This is v minus and this is v plus, but I wrote them down in the form that kind of says that the function v has 2 branches, and that's about it.